Let's talk for a second. Today's class, we're going to discuss rotational dynamics. So how torques applied to objects turn into angular acceleration. Now, you've already used in the warm-up the equation that I'm about to show you. So that equation part's not going to be crazy or wild or new. Okay? I'll show you where it comes from, if that's interesting. And then we're going to do a couple of examples to really see how this works and think about some unique factors. But one thing I want to talk about first is that in the warm-up, which was this, we said that this force at the end, which I think was actually F, but I can't put FF because that's friction. So I just labeled it A again. FA, force A, you said it applied no torque and therefore did not cause any angular acceleration, which is absolutely correct. But it is still a force being applied to this, let's say it's a door on a hinge. Now, it's not going to cause the door to rotate at all, but if I have Hulk-like strength and I pull with a force A that's really, really, really strong, what effectively will happen eventually to that door? I'm going to rip it off, right? And that force is going to create a tangential acceleration, and I'm going to drag the door that way, right? So it's important to remember that just because a force has no effect on the angular acceleration, it's still a force. If it were to be unbalanced, it could still cause regular, old-fashioned tangential acceleration. So we're going to make a note of that in our notebooks so that we remember that tangential acceleration is caused by forces that are parallel to the radial line. So you might not have thought very much about the radial line. You were like, well, this is in line with the pivot. You didn't really think the words maybe radial line, but the radial line is from the pivot through the object to whatever point I'm talking about. Whatever point the force is being applied to, that's the radial line. So with this straight rod object, the radial line is in line with the object. So you knew, well, since the force is in line with the object, that force is parallel. And these forces, which were perpendicular, we're actually going to do the angular acceleration bit. Okay? So these forces, which are perpendicular, cause angular acceleration. Now, that's really easy to spot if it's a nice linear object. But what if it's not? What if instead I have this amorphous blob that I've drawn here? So for my amorphous blob, I don't know what the density of it is, but I found the center of mass. It's located right here. And I'm looking at forces that are being applied to 3 different particles inside of my blob. So my blob is a solid object made up of particles that have mass. Okay? This desk is made up of particle board. If I isolated one little chunk of wood inside particle board after it's been shredded and compressed and whatever, made into this desk, that's what I'm talking about, right? One important thing to note is where is the radial line? You might not think of it much in an object like this because it's a straight line. You're like, I know where it is. I don't need to draw it. But for an amorphous blob and random dots strewn throughout, make sure you're thinking about where that radial line is because I have 3 forces in 3 completely different directions. Some of these forces are parallel. Some of these forces are perpendicular. Some of them are combinations. But I only know that because I've already drawn their individual radial lines. And they are not all the same or pointing in the same direction. So a radial line, in case we need to define it, is from the pivot to the location of the force. So my force for my amorphous blob here is occurring at these 3 particles spread throughout the object. Okay? So in my amorphous blob, I've got, let's start with mass 1. Mass 1's being pulled on with F1. Right? This angle here is very clearly not 90 degrees. I don't know what angle it is, but it's not 90. So that means some portion of the force, hold on one second, some portion of the force is going along the radial line, and some portion of the force is going out perpendicular to that radial line. Yeah, question?
90 degrees to what?
What?
You said it's 90 degrees.
No, I'm saying it's not 90 degrees.
So like what though?
To the radial line, this dashed line that I drew. When I drew F1, my aim was to make it not look 90 degrees away. So this F1 has components of its force that are in line and parallel to the radial, and components that are perpendicular. So F1 is causing angular acceleration and tangential acceleration. F2, the entire thing is in line with the radial, so this one's only causing tangential acceleration. That's the only thing it's causing. It is causing a movement of the center of mass. I'm assuming that this amorphous blob is free to roam, is maybe out in space. It's got no gravity acting on it, so whatever force is being applied there is actually going to move the object that way. Force 3 is at a 90-degree angle, so this force would only be causing alpha. It's only causing angular acceleration. So F3 will not make the center of mass move, but it will make sure the object spins. Okay? So this is important to know. We're going to talk mostly about torques being applied to objects, and they're going to start spinning, and that's great. But as a reminder, any force that's applied to an object, if it's unbalanced, can cause, if the object's able to move, movement of that center of mass. So, if we look at these forces, F3 is going this way. The component of F1 that's in the same direction is going the same way. So, this thing's going to be spinning around clockwise, right? This whole thing would be spinning clockwise. If I look at the tangential acceleration, the forces that are going to cause tangential acceleration, one's pushing it this direction, up and to the right. The other one is pushing it down and to the right. So I don't know what the amounts of these things are, but I can make an assumption that it's at least going to go to the right. I don't know if it goes up or down, but it's going to go to the right. Okay? So, different forces applied in different locations at different angles can cause different types of acceleration. So don't just like get in your head, okay, this force, because it's along the radial line, it doesn't do anything at all. No, if this door had been free to move, it would accelerate the door's center of mass to the right. Forces still do things. So, parallel to the radial line is going to cause tangential acceleration. If possible, that will mean the center of mass is going to move. Perpendicular to the radial line is going to make a torque causing it to rotate. Okay? That's the difference. So, if I have this stool here and I want to push it that way, right, this direction, if I push on the top, oftentimes I'll get it to rotate instead because I applied a pretty heavy torque pretty far away from the center of mass, and I applied it perpendicular to the radial line there. If I wanted to get the object to move and push it on the center of mass, now it doesn't rotate because my force didn't apply a torque. It applied just a force that moved the center of mass since it was free to do so. All right, with that, let's talk about Newton's second law. So Newton's second law says F equals ma. Pretty standard stuff there. Force equals mass times acceleration. Well, in fact, I want to change this into the rotational equivalent of force. So a force by itself can't actually cause this, but if I change A to R times alpha, now I have alpha in my equation. Again, this is nothing. This equation does not do anything. Force cannot cause an angular acceleration unless it's a distance away. So right now this is a nothing equation. To make sure that instead of force causing angular acceleration, it's a torque causing angular acceleration, I'm going to multiply both sides by r. So that makes Fr is equal to mr squared alpha. Fr is torque, and mr squared is moment of inertia. And that is how I get Newton's second law rotational. So, That's the rotational equivalent of Newton's second law. It's not new or different. Force equals mass times acceleration. Torque is the equivalent rotational force. Moment of inertia is the equivalent rotational mass. And angular acceleration is the rotational acceleration. So this is the equation we're going to use. And let's do that. I have our first example here. So in space, I have launched this object and I need it to spin. So I have two rockets. This is rocket 1. They're attached by a massless 90-meter rod. This is rocket number 2. The rockets are not the same mass. This one's 200,000 kilograms. This one is 100,000 kilograms. This one, make sure I do it the right way, yeah. Exhausts that direction. This one exhausts that way. Each individual exhaust on the rocket can create 50,000 newtons of force. So, if the rocket thrusters are turned on, I want to know what is the angular speed after 30 seconds. All right, how about it? Yes, you do, not me do. You do. You can do it in your notebook and your notes. You can do it on the whiteboard. Think about where to start, what information you might need. Come up with a problem-solving strategy.
What is that at the bottom?
This is the fire coming out that's creating the thrust, or this bottom. This is the mass of this rocket.
What does that say?
100,000 kilograms. 100,000 kilograms for this rocket, 200,000 kilograms for that rocket.
And the force is that 50?
50K. I wonder if you need some glasses.
Oh, I have contacts.
Are you wearing them?
Yeah, but it's like the glare.
You could also sit closer, Christian.
Yes, pretty much.
It's good. It doesn't need it. Are you fine with zero? Why do you need to because the research organization
So their mass is like 60 meters.
German thing given already, right? I agree. Always terrible. I would agree with that, Stephen, if you got every assignment, every test. So maybe they look for perfect direction. It's possible, maybe it's possible that you try it and then still study it.
It might be 60 meters from the left side.
Well, again, laziness is a choice.
I'm pretty sure I got this.
Laziness is a choice.
It's like 60 meters.
Yeah, 60, yeah.
It is not in the center. Has more money. Calculated it. Where did you get? Yeah, that's fine. They're pretty simple numbers.
One is pointing this way.
Okay, so then it should be what? Does this count as any of those
No,
objects?
that's a torque. So we had a torque, now we need I. One third ML, one third ML.
That's an idea, but again, it's not a zero axis here, you have to base it on one of the shapes. This isn't one of the shapes, it really models out one barbell with two masses.
That's three and a quarter.
So I've just.
One third, three and a
This equation,
What do you do?
it's just the sum of each individual masses.
100K times 81. What's 100,000 times 81? Why is
And then I just add together the moment of inertia from 100K.
Wait.
You have so much more room for activities, aka problem solving.
Wait, 8, that's 8.
This wasn't here, you know?
So 4, just 4.
So what have you done so far?
Wait, it's just 8. The right one.
That's the torque of the right one. So you did 50,000 as the force.
90.
And what's this? So is that the torque? Well, then this isn't the torque. You did a force times a moment of inertia. You've done this. F
We need angular
is
velocity.
equal to, or F times the
No, it's no, this one is
Wait, what is heavier?
What do you think inside? What's going on?
Plug it in, right?
So the question is where radius is dependent on the pivot point. So where on that rocket ship are they going to pivot
Plus
from?
8. Plus, we all look 18 points.
Well, if it's like you're saying where they're connected. Well, not necessarily, because there can't be 2 points. Because think about it this way. When I'm asking for a pivot point, I'm saying if I stare at this object, this spot should. Is it the middle though? If it's an object completely free to rotate without a pivot or an axle on it, it will rotate at its what?
In 30.
But what location will it
It's
rotate at?
really heavy.
It's center of mass. Center of mass. So is the center of mass of this rocket ship in the center? Because these are equal masses?
No, that's what we got.
It's gonna be tilted, and I probably need to figure out where it is.
4.5 mil
Yes?
over 80.
Yes.
Where do you put the R?
My YouTube video, they're gonna love me. They're gonna be like, this girl wasn't even on screen for half the time. It's okay.
0.25.
The angular into the velocity. The angular velocity.
Okay, wait, there should be negative. Wait, no, that's,
I'm just like
okay, then you add
doing
this
it
with
manually
the
without a calculator. So it takes a second time.
All right. I'm gonna work through this problem with you guys now. My first question would be
It's like 10 minutes. No, not 10. 2.
2 minutes. All right, 2 minutes. I have 2 minutes.
This seems to be too slow, but the thing is that's heavy.
Don't come over there. Is that what you said?
Wait, I'm
You have
where do you get it? I got 0.5.
you get one word.
Okay. So this here you're saying that
0.5 radians per second.
I agree with all of that. This would be your torque, and this would be the moment of inertia, and we're solving for this.
Yeah.
My issue is that you're doing it for one. Are you going to then add the second one? Both rockets are rockets.
Yeah. Did you
So
derive
your
this
torque
from
calculation is going to give you an angular acceleration from one of the rockets.
Have y'all?
The 200,000 one that's has 16 meters. Where'd you get that 16?
I don't know.
Yes, but is the big rocket or the small rocket 60 meters away from the center of mass?
I think it's
You're saying that the center of mass is here or here?
plug it in and you
It's over here, right? So that one should be. You can do that math and then do it for the other rocket and add them together. If that's fine, or you can just add them together. I would. But yes, it should be 30 instead of
What?
yes.
The moment of inertia of the paper in the Let me just rock it out.
Almost, you get FP over FI.
We have to use the integration. No.
Because it's
So these are modeled as like objects. This is just like you can send this to John.
Oh, right, and you knew research poster?
So I wouldn't.
I got like 1.5 because I saw the video. I saw that. This is the guy. This is the guy after research. Vince, but the father. I researched the father of Vince. What's 45 mean?
Oh.
I don't know. I honestly don't know.
In my
No,
but we got 4.5 but our denominator was like, is it?
Yeah, I got 4.5.
Is it 1/3 L squared? I got 4.6.
Well, you're trying to find angular acceleration, right? So you want to see how fast or how much it takes to
You can understand it.
angular acceleration. Okay, so this is angular shape, right? It's not who.
Wait, but you don't know the.
It's here, it's not
Hey, but you don't know what
It's
the.
these G submasses. So when I have full mass,
I thought you were
next to somehow, I use this equation.
I mean, is it a negative?
But did it get 0.6? 0.1?
She didn't provide that?
Wait, for this? No, you have to.
No, I'm talking about the
Yeah.
So how are you supposed to do 4.5 and a bunch of squares?
Okay,
That's the
problem.
You just do FR squared.
7.5.
Where?
Okay,
You know, like normally, right? You're rotating a point.
Okay,
So you and you add to the inertia of the rod plus the inertia of that point some distance away, right?
Or no,
But you don't touch that percent assuming the rod has measured.
Oh, plus, it's like not.
I did the average, and then I did it for the other.
All right. Now I'm going to do this because that was 2 minutes. All right, so if I'm looking for angular speed after 30 seconds, right, I could even start, if I need help with my problem solving, I could say I'm looking for a final speed. I know the initial speed is 0. I know the time is 30 seconds. If I start thinking about equations, I really easily come up with this one. But the thing I need to know that I don't is angular acceleration. So I'm going to have to find that. The equation I have for angular acceleration is that it's equal to the net torque divided by the moment of inertia. So now I need the net torque and the moment of inertia. Okay, well, as a really important reminder, something that I would make sure I've starred and remember really, really well, moment of inertia and torque are entirely dependent on the location of the pivot point. The amount of moment of inertia that I have, the amount of torque that forces are applying is dependent on where this object is spinning around. In this case, that's going to be the center of mass, which is going to be skewed towards the larger rocket. So the first thing I had to do was figure out where is the center of mass. So I have an equation for that. XCM is equal to 100,000 times 0 plus 200,000 times 90 divided by 300K, which is equal to 60 meters. So rocket 1 is a distance of 60 meters from the pivot, and rocket 2 is a distance of 30 meters to the pivot. So that's the first thing I had to do. The second thing I had to do was find my torque and my moment of inertia. So for torque, that's just the force, 50,000 times 30 plus 50,000 times 60. I get 4.5 Newton meters.
Whoa. I got 5.4.
That's the moment of inertia.
Oh, yeah.
Yeah, I'm doing torque first. So, for a moment of inertia, this seemed to be a struggle, so let's pay attention as we go through questions and pay attention to when they want us to use a shape and when they want us to use separate masses. So this is an example of when they want us to use two separate masses, and for that I just add together each mass's moment of inertia. So 100,000 times 60 squared plus 200,000 times 30 squared, which is equal to 5.4 times 10 to the 8th kilograms meters squared. Questions about either the torque or the moment of inertia? Well, if I divide these two numbers, I get an angular acceleration. What did somebody get? What's the angular acceleration? No. What 4.5 million divided by 5.4 times 10 to the 8th gets me? No, it really does not. We don't use fractions. We don't use radicals. Keep those in math class where they belong. Yes?
Is it like 8.33 times 10 to the 8th?
Yes, I'm going to write it not in scientific notation, but you're completely correct. Oops, rads. For a second. So 0.00833. To get the final angular velocity, my initial was 0 plus 0.00833 times 30 seconds. I get 0.25 rads per second. Questions? Okay, this is the kind of question I expect you to be able to do. To prove it, let me give you another one. All right, I own a propeller plane. I actually don't own it. But if you think propeller planes, those must be completely foreign and old and nobody uses a propeller plane. I've ridden on 4 propeller planes this calendar year. I rode one up to Lukla, which is at the base of the Mount Everest Base Camp hike. One on the way back. That one was landing on a steep hill that's supposed to be the most dangerous airport in the world. I lived, yay. The second set was flying to a remote island in the Maldives for my vacation after I climbed to Everest Base Camp. Those planes landed on the water. I didn't like that. I would prefer to always land the planes on the land. The water seemed really scary to me, but that's neither here nor there. Propeller planes still exist. This particular propeller plane that I have has a propeller that is 2 meters long. It weighs 40 kilograms. And to take off, I need to get to a speed of 200 RPMs. 200 RPMs. That's the speed I have to get to. So from cold start, I have to get my propeller blades spinning at 200 RPMs for me to be able to take off in my propeller plane. My engine provides a torque of 60 Newton meters to my propeller blade. Okay? We talked about this on the last question. We have to pay attention to when they want us to use separate masses versus that when they want us to think of something as a single object. If this was the start of an FRQ question, this is the diagram given and the information given. Should I use this as a shape? If so, what shape? Or separate masses? What do we think?
Separate masses.
Why do you say separate masses?
Because you have a 40 on this side.
I said the whole thing's 40.
Oh, I don't know.
If I wanted to say it was separate masses, I would have to then say, okay, I'm going to go separate that one mass that they gave me. So everybody see how that kind of automatically gets complicated and you're like, well, maybe I'm doing it wrong. Right? They gave me one mass for this object. So I probably should see if there's a shape that this could actually be. If I think about this propeller blade being longer than it is wide, what shape would this effectively be? A rod. Is it rotating about its center or about its end? center. All right, get started, solve my problem. Wake up and solve my problem.
Wait, so you're trying to get to 200 RPM. What is the total?
The torque's 60. So I want to know how long it's going to take me to get to 200 RPM.
Oh, then what's that? Oh, wait,
To reach 200, yeah.
Okay, during the that's side.
Yeah, that's just the unit.
wait, the entire thing is 40 kg? That one. Wait, is that 1 kg or the what time is it? Oh, the entire thing 40 kg or is it?
I did it in a weird way.
Okay, got our kinematic equations.
Wait, so it's just
Yeah.
60 divided by.
So how do I solve for acceleration?
No, T equals 200.
The equation we learned. You can start with this equation. There's a simple thing you can start with. Just alpha equals, you have it right there, alpha equals torque over I.
Same.
It's the exact same thing.
Now give you your.
Now,
And
find
that's
angular
perfectly fine, but also one thing to consider, just thinking about it, what units will this alpha be in when you calculate?
No, what?
What are the units?
Wait, oh, no, not torque. I meant time.
So it's circle, so it's radians per second squared.
200 I.
Problem is this in terms of radians per second.
Fine, bro, it's
Ah, so I probably need to do some.
T equals I, right? Yeah.
So 160.
So, we can find. Wait, which T? Is it a capital T?
You found I.
Oh, wait, no.
Algebra software is what's this supposed to be then? The final velocity is equal
This
to
is
I.
singular object.
Okay. Just like you have found alpha, yes? Okay.
What's the
I have a silly question.
No,
Why are the units that? Okay, what are the units?
No, it's a rod, right? So 1 third. It's a 1 third.
200.
Oh,
Oh, shoot. What's the problem? Anybody see the problem? I see the problem.
wait, I converted it here, but I didn't convert it there.
L squared, so 112.
Did you already solve it?
That's a silly question.
Wait,
No, 5 and L squared.
9 over 2? Okay, I agree with that. But what's the
Oh!
wait, what do you guys, that's 200. Did you get 44.44?
I got that.
40?
Yeah, like, I just don't know. I'm just remembering which one. Oh, wait.
Wait, no, that's not. Wait, but the units have to be RPM.
Yeah.
Wait, no. 112 squared.
Yeah, convert RPM into radians per second, and then your acceleration was
He can solve that.
Wait, but wait, you're solving for T. Oh yeah, I got 4.6. Wait, for some reason, that was
It's 725 over the last.
Where's the center?
Yeah.
Is it in? Oh, water. No. As long as it's like that.
No, I didn't do anything. This
In the y-axis.
equals 4.5.
Wait.
Here's the highlighted issue. First off, this, there'd still be rods on. And the issue with this method is that I can use torque as a whole. And that's why you're like, that's not right? See how that's one of the issues with doing it that way. It's not that you're wrong, but if I don't give you the right thing, that doesn't work.
Yeah.
Radius, it's still 2.
Okay, 2 power 50.
Still 2.
200 times power pi over 30. I times pi over 30. Divide by 4.5. What are you looking for? Your mom.
No, you don't forget.
After the angle equals.
Evil.
4.6.
Yeah.
Yes, sir.
You got that?
Oh, so we converted it to radians per second. Radians per second.
Maybe me and like
Apparently it's supposed to be
yeah, that's like old jokes.
I thought that's what.
Wait, isn't this just? Isn't it just a figure of Y-O-M? Wait, it's just not. Oh yeah.
Oh, young.
This divided by time, what do you
Oh, that's me.
This divided by 24/7.
That's how
This
it's
divided by like,
All right. Check your answer. If you haven't gotten that far, look over and I'm going to explain what I did here. So, first things first, check your units, all right? Angular acceleration is always going to pop out in terms of rads per second squared, which means that my W needs to be in terms of rads per second squared. Now, as a reminder, in kinematics world, if I was just doing a kinematics problem and they gave me RPMs and a time in minutes where I converted it to minutes, and I needed revolutions, I can do a whole kinematics problem in RPMs. I could do a whole kinematics problems in RPSs. I could do a whole kinematics problems in revolution per day, as long as I keep it the same. So the issue is not that it's RPMs and it has to be rads per second. The issue is that solving through torque, I'm going to get an acceleration that's in rads per second, and they have to be the same units. You could have, weirdly, converted acceleration into RPMs and then solved it, and it would have been fine. You still would have gotten the right time. But just keep an eye on those units. Whatever kinematic equation you're using for angular has to be in the same terms. This was true in linear world too. Kilometers per hour, miles per hour, meters per second, but it had to be consistent. So, first things first, I converted my final angular speed into rads per second. I then had to find the moment of inertia. This is a rod rotated about its center. So that's 1/12 ml squared. Calculated that. Angular acceleration is torque divided by moment of inertia. I was provided torque. So I got 4.5 rads per second. Ooh, squared. And then I used a kinematic equation to solve for time. Questions about this? All right, the last thing we're going to go over is this extra thing that we need to think about. So this is a dynamics problem. I would add up all the torques, find the moment of inertia, and I can do some calculations. But when we talked about dynamics in a linear respect, we started with this, then we looked at ramps, and in another type of problem that we looked at were Atwood machines. As I hear so many excited sighs that are excited for the possibility that this is going to present. Now, when we talked about Atwood machines in linear land, we always said that these were on a massless, frictionless pulley, and there was a reason for that. It mattered. We're about to see that having a non-massless pulley is going to cause my acceleration to change, okay? And here's the stipulation that we have to be aware of, the one that they're going to use. It's called no slipping. So they're going to say I have a massless pulley, and there is no slipping between the rope, string, rod, or wire, whatever it is, and the pulley itself. That means that every second, as it turns, the rope and the pulley are together, basically making the pulley part of this connected object. The pulley has to be moving at the same speed, has to be accelerating at the same rate. They are now touching and therefore have to be going at the same speed and the same acceleration. If the rope were to slip, then for an instant, the pulley and the rope wouldn't be attached and they might not be going the same speed. But if there's no slipping, then the understanding is that the rim of the pulley and the rope are connected and therefore moving together. That is the stipulation. So I can say this. The velocity at the rim of the pulley, so the outermost edge, the velocity at that edge of the pulley, would be equal to the radius of the pulley times the angular velocity of the pulley. And is also equal to the velocity of the rope and the velocity of the mass. The outside edge of the pulley has to be spinning at the exact same rate as the speed of the rope and the pulley, or the rope and the mass, because they're now all connected and touching at all times. So where you go, I go. Same thing goes for acceleration. If the speeds have to be the same, then the accelerations do. So I can make this statement here.
Is that a W or a C?
This is a W. Angular velocity. So keep that in mind there. Okay? So this stipulation is something we can use when solving pulley questions. So that's what we're going to do now. I'm going to walk you through this one. The last two examples, I kind of let you guys go on your own. This one, I'm not going to do that. I'm going to walk you through step by step so you can see how this would be solved. All right? So again, the velocity at the edge of the pulley, the acceleration at the edge of the pulley has to match the rope, has to match the mass. So when I know the system, this Atwood machine's system's acceleration, that's the acceleration at the edge of the pulley. So here's my example. I'm going to change it up. I have a bucket. That's the handle of a bucket. That's the bottom of the bucket. This is a 2 kilogram bucket. This pulley weighs has a mass of 1 kilogram and a diameter of 4 centimeters. What I want to know is, notice there's nothing on the other side of this, so in theory, this bucket is free to fall. I want to know how long for it to fall 1 meter. That's the question I'm asking. How long for that 2 kilogram bucket to fall 1 meter? Now, before I dive into this, let's just conceptually think about it. If the pulley was massless, what would be the acceleration of the bucket downward? G, right? 9.8. If the pulley were massless, then there would be no tension in the string, and it would just be falling. It would be in free fall, no big deal. With the pulley having mass, you can think of it in a connected object scenario as an additional mass in the system. So do you expect that this bucket is going to fall faster or slower with this massed pulley? Slower. And we're going to see that in just a second, but that's what I expect to happen. All right? One strategy when solving things like this, you should think of it as having a system of 2 equations. Okay? When you have this scenario with a pulley and an object that's falling, you have 2 Newton's second laws. You can write out Newton's second law in rotational, and you can write out Newton's second law in translational. Okay? You could start solving either of these, and you'll realize in this case, our case, based on what we know, we're going to need both of them. But just as a reminder, when I start this problem, as long as I'm really well aware of the fact that the pulley's there, and it's going to be causing a problem, as As long as I'm aware of that, then I'll find that I can use both of these equations, and I'll probably need to work between them. So I'm going to draw real quick a free body diagram for the bucket, just so we're all clear on what forces are acting on the bucket. So F, G, and then a force of tension. Before we get started, is that force of tension equal to Fg? When is it equal to Fg? What's the stipulation there? And what? Maybe, yeah. Probably not, no. Moving at a constant velocity or at rest, right? If it's accelerating, then F net equals mass times acceleration. I have a problem there. So this is going to be Ft minus Fg. So we'll go ahead and put that up there. That's what that is up there. So the force of tension is not equal to mg. My life would be so simple if it was, but it is not. So moving on. I'm going to work the rotational side first. So my angular acceleration is equal to the torque. The torque is caused by this rope pulling on the pulley, right? The rope is attached to the pulley, so the tension of the pulley is going and pulling on it. So the force would be the force of tension. The radius would be r, the radius of the pulley, whatever that is. In our case, 2 centimeters. It's a very small pulley. I've drawn it much larger than it actually is. What is the moment of inertia? This is a pulley. Kind of looks like what type of shape? A disc. So what is the moment of inertia for a disc? 1/2 mr squared. So 1/2, I'm going to say this is the mass of the pulley, r squared. Okay, well, I don't know what the angular acceleration is, and I don't know what the tension is, so I currently can't solve this equation. I'm going to change it, though, so that I have regular acceleration, so I could set these two equal to each other. That would be cool. Or so that at the very least, since I'm solving for tangential acceleration, how fast the bucket's going to fall, I'll at least be solving for that. So how do I convert angular acceleration into tangential acceleration? I multiply by r. I shall do that. So tangential acceleration is equal to Ft r squared over 1/2 mp r squared. R squared's canceling out, and I've got that there. All right, that seems pretty cool. I've got this. Over here for the linear side, this is, just as a reminder, the mass of the bucket, so we don't get those confused. All right, my goal is to solve for A. What do you want to do? I have these two equations. I'm staring at them. They're gorgeous. Set them equal to each other and then solve for Ft. We could do that, right? Then we'll solve for Ft and we could plug Ft back in to an equation to solve for A. That would be good. A little bit of a simpler way to do it, so that I can just solve directly for A, is to solve this for Ft. Then I can plug Ft in here and solve for A. So that's what I'm going to do. Either way would work. This skips a couple steps, so that's what I like to do it. Ft is equal to, make sure I don't mess this up because I did in first period. Ft is equal to 2 A MP.
Wait, I have a question. How did you get the R on the top to be all squared?
What?
Like the R on the side, how did you get that?
I just said I'm multiplying both sides by r because angular acceleration times r is equal to tangential acceleration, right? This statement up here, A is equal to r alpha. So I just chose to. As long as I do the same thing to both sides, I'm allowed to do whatever I want. Those are the rules of math. Yeah, Shraj.
Why is it 2?
That's why I keep doing that. It's 1/2. I've done that all 3 class periods today. Every single time I stare at it for a long time. I'm like, I know it's not 2. I know I've done this before. It's not 2. And then I do it every single time. It's so sad. Okay, I'm going to be better. All right, that's that. One thing before I go and plug this in, though, I want to make sure, because we've forgotten about something that we haven't added in at all. Okay, and that is direction. So if the bucket pulls down on the pulley, which way is the pulley going to rotate? Clockwise, which is the positive or the negative direction? Negative. So my acceleration is going to be negative, making all of that negative. So keep in mind when you're doing the rotational bit, this direction does matter, okay? Even if you're like, well, wait a second, but clockwise and I don't really like it. Remember when we do outward machines, we always determined that maybe this direction is going to be positive or negative. In our case, we're saying this is the negative y. So the bucket should accelerate negatively. That means that since the pulley is spinning that way, it also has a negative acceleration. So whether you think of it through terms of clockwise or counterclockwise, or just in terms of an outward machine, it has a negative acceleration either way. All right, plugging that in. Acceleration is equal to, I'm just going to put mb back over here. mb is equal to negative 1/2 mpa minus mbg. Now it's just algebra. So mba plus 1/2 mpa is equal to negative mbg. What? I'm going to keep going.
MBA on the other side.
I just multiplied it back over. Because doing that all in a fraction seemed like a horrible idea. I didn't want to, so I'm not. All right, so I get acceleration times mb plus 1/2 mp is equal to negative mbg. If I divide, my acceleration is equal to negative mbg over mb plus 1/2 mass of the pulley. What would happen if the mass of the pulley was 0? If this term completely went away, what would be the acceleration of the bucket? G, just like we said it would be at the beginning of this question. If the pulley is massless, then this portion goes away and I just have an acceleration of free fall. The more massive the pulley is, right? The larger the pulley's mass is, the less acceleration that I'm going to have. The smaller fraction of g that I'm going to have. Okay? You can plug in the actual numbers and get the answer to this and then find the distance or the time it takes to fall. But this is what I wanted to show you. Okay? Something that you can use. You might not think of it initially, but you can use the fact that if you have the no slipping condition, then you can both solve for rotational acceleration tangential, like the acceleration at the edge of the pulley, and the linear acceleration, and those have to be the same thing. So you might not have to do this in a question that you're asked, but it's something that's at your disposal. And at least the rule of it is probably something you're going to need. The fact that the linear acceleration at the edge of the pulley has to be the same as the linear acceleration of anything attached. All right? Okay.